Hi there, Mr. Sutton here, bringing you the BC Calculus 7-8 Extra Practice Number 6 solutions on interval of convergence. To find the radius of convergence for this non-geometric series, we're going to use the ratio test. So we've got limit as n approaches infinity of absolute value of, and now I need the n plus 1th term divided by the nth term for this expression. So we're going to have x to the 2 parentheses n plus 1 over n plus 1 factorial. That whole thing is just the n plus 1th term. Down here we have the nth term, which is basically the general formula they have in the sum and. Now same change flip. This is going to be rewritten as x to the 2n plus 3, and we're also going to multiply that by n factorial. Downstairs we've got n plus 1 factorial times x to the 2n plus 1. I can reduce these a little bit. These x's I can reduce if I subtract the exponents. I'll have just an x squared in the numerator. And if I reduce these factorials, I have just an n plus 1 in the denominator. So in the numerator then, x squared, and downstairs, n plus 1. As n approaches infinity, since x is treated as a constant in this situation, only the denominator is growing. So that means this goes to 0, because it's bottom heavy. And since 0 is always less than 1, and this converges if the ratio is less than 1, since this is always true, this means that my radius of convergence, since everything is going to make this converge, the radius of convergence is going to be infinity. If you go forever in both directions from the center, you will find x values that make this converge. To find the radius of convergence on this, first let's check to see if this is a geometric series. It's not. It almost is, but we have this n out in front that's not exponential, so that's an issue. That means we're going to have to use our ratio test instead. So I've got limit as n approaches infinity of absolute value of the n plus 1th over the nth term. So I have n plus 1 times x plus 3 to the n plus 1 all over 5 to the n plus 1. So that whole thing is the n plus 1th term. We divide that by the nth term, so this stuff with no change. And then we do a little same change flip, multiply by the reciprocal. So we've got n plus 1 times x plus 3 to the n plus 1 times 5n, or 5 to the n, that is all in the numerator. In the denominator, we have this 5 to the n plus 1, this n, and then also an x plus 3 to the n. Reducing things a bit, these 5s can reduce to give me just a 5 in the denominator. And let's see, can't do anything with the n's, but the x plus 3's, we can reduce those to get just an x plus 3 in the numerator. So when the dust settles, upstairs I've still got an n plus 1 and an x plus 3. And downstairs I've still got a 5 and an n. All right, so now as n approaches infinity, we can ignore this plus 1 that's next to the n. Not the plus 3 next to the x. This is all treated as kind of a coefficient, but in here, as n goes to infinity, we can ignore the plus 1 that's kind of attached to it. So this then just ends up being x plus 3 times n over 5 times n. N's cancel, so you just end up with x plus 3 over 5 for your nth ratio. And now for this series to converge, this ratio needs to be less than 1. To find the actual radius of convergence, we need x inside this absolute value to have a coefficient of 1. So to get that, I'm just going to multiply both sides by 5. So I have x plus 3 absolute value less than 5. And that means my radius of convergence is this 5 over here. On this one, we're trying to find the radius of convergence for this series. So this is a little bit odd. We have this f of x series that's just x to the n. But then we have this integral of all that. So we want to find the radius of convergence for this integral function right here. So to do that, let's just rewrite this series with its antiderivative, which is going to be x to the n plus 1 over n plus 1. And we'll just keep the limits of integration, the limits of summation there. So now this is not a geometric series. To figure out radius of convergence, I am going to need the ratio test here. So I'm going to have the limit as n approaches infinity of the absolute value of n plus 1th version of this over the nth term version. So that's going to be x to the n plus 2, or n plus 1 plus 1, over n plus 2. That's the n plus 1th term. The nth term is just going to be x to the n plus 1 over n plus 1. So that's kind of confusing. The nth term is having an n plus 1, the n plus 1th term has an n plus 2. Anyway, same change flip on this. We have x to the n plus 2 times n plus 1 over n plus 2 times x to the n plus 1. We can clean this up a little bit. These x's reduce. Subtracting my exponents, I just get an x to the first power upstairs, and that's joined by the n plus 1 that's already up there. Downstairs, all that's left is the n plus 2. As n goes to infinity, I can ignore this plus 1 and this plus 2, so we basically just have xn over n, which just reduces with those n's to x, absolute value of x. So this is just going to come out to, let's see here. Well, we've pretty much got everything as simplified as it's going to get in there. So we just have to take this ratio and set it less than 1, because this whole series converges if the common ratio is less than 1. And that means since we have a coefficient on x of 1, this is the key here, that means that whatever is on the other side is the radius of convergence. So in this case, the radius of convergence is just going to be this 1. And just as a small follow-up point of clarification, although you could leave limit as n approaches infinity around here, you don't actually need it, since once those n's are gone, you've essentially applied this limit. To find the radius of convergence for this non-geometric series, I need to use my ratio test. So I have limit as n approaches infinity of absolute value of, and now we have a fraction here. Up top we have the n plus 1th term, so that's going to be n plus 1 factorial times x to the n plus 1. Down below we just have the nth term, so n factorial x to the n. So overall then we're just finding the limit of the ratio. So let's see here. We can reduce this a bit. These factorials reduce to just give me an n plus 1 in the numerator, and these x's reduce to give me just x in the numerator. And there's no denominator now. So as n approaches infinity, this whole thing is going to infinity, which means that the radius of convergence of this thing, well, since infinity is greater than 1, and this thing only converges if the ratio is less than 1, that means there is no radius of convergence. It doesn't matter how far you go in whatever direction, you're not going to find convergence. So we would say the ROC for this one is just 0, which is to say the only place you will converge is at the center of this thing, which also happens to be 0. On this problem, we want the interval of convergence for this series. Since this is geometric, with a common ratio of sine of x over 2, we just need to take that common ratio, the absolute value of that, set that less than 1, and solve for x. So we have absolute value sine of x over 2 less than 1. And multiplying by 2, I have absolute value sine of x less than 2. Now, you can think about trying to take inverse sine, but let's just think about this logically, what's going on here. If you take the sine of something, what kind of outputs are you going to get? Well, you're going to get something between -1 and 1, including -1 and 1. So whatever you plug into sine, you're always going to get a number that is less than 2. So that means since this is true for all x values, that means our interval of convergence is actually all real numbers. So we can just write -infinity less than x less than infinity for our interval of convergence. On this problem, trying to find the interval of convergence, this is a geometric series. It's kind of the poster child of all geometric series. Since this is geometric and our common ratio here is just x, we can find the interval of convergence by setting the absolute value of our common ratio, absolute value of x, less than 1, and then solving for x. So solving for x, you're already almost all the way there. We can just rewrite this without absolute value by writing -1 less than x less than 1. And this is going to be the interval of convergence. Since this is a geometric series, that means that we are guaranteed that the endpoints are not part of the interval of convergence, so I don't even need to test out -1 and 1. I am just done. To find the interval of convergence on this problem, which is not a geometric series, I'm going to have to use the ratio test. So I have limit as n approaches infinity of absolute value of, and I have the n plus 1th version of this divided by the nth version. So n plus 1, we've got x minus 1 to the 2 parentheses n plus 1 minus 2 over 2 parentheses n plus 1 minus 1 factorial. So that's just a big mess that we're going to have to clean up in a little bit. Basically, we just plugged in n plus 1 for every value of n there. Down below, it's a little bit nicer. It's just the nth term. So it's just all the stuff you see here, which really isn't that nice by itself, but it's better than what we wrote up here. So now same change flip and do a little distributing and collecting of like terms. In my numerator, I've got x minus 1 to the, we'll call this, well, let's see here. This is 2n plus 2 minus 2, so this is just 2n. And we've also got this 2n minus 1 factorial up there. Downstairs, this is going to be 2n plus 2 minus 1 inside the factorial. So that's 2n plus 1 in the factorial. And we also have this x minus 1 to the 2n minus 2. Okay, so let's reduce a little bit more here. So this one's a little bit tricky to reduce, but we're going to reduce these exponential terms by subtracting the exponents. So I would have x minus 1 to the 2n minus 2n plus 2. So that gives me an x minus 1 squared in the numerator. And now let's tackle these factorials here. These are a little trickier. It helps if you recognize that 2n plus 1 factorial is really 2n plus 1 times 2n times 2n minus 1 factorial. So if you cancel out the 2n minus 1 factorials, you still have the 2n plus 1 and the 2n by itself in that denominator. Now, as n approaches infinity, we can ignore this plus 1 next to the 2n there. So we essentially have x squared minus 1 squared, or x minus 1 squared, no other square in there, over 4n squared. The key here, though, is that n is the only thing that can change. X is considered a constant, so you've essentially got a constant over something that's growing. So this is a bottom-heavy function, which means that as n approaches infinity, this is going to reduce down to 0. Now this series converges if my nth ratio, which is what I just found here, is less than 1. So normally we would have an absolute value with an x in it that we would set less than 1 and solve for x, but we just came up with 0, and 0 is always less than 1. That means this is going to converge for all x values, no matter what, because no matter what you plug in for x, this is still going to be a true statement. So that means that our interval of convergence, we're going to have negative infinity, less than x, less than infinity. To find the radius and interval of convergence on this one, since it's not a geometric series, we're going to use the ratio test. So I have limit as n approaches infinity of, and now we need the n plus 1 over the n term here. So we'll have 10x, all of that raised to the n plus 1 over n plus 1 factorial, divided by just the summand as it was originally written. That's just the nth term down there. Same change flip. We've got 10x to the n plus 1 times n factorial upstairs. Downstairs we have n plus 1 factorial and 10x to the n. Reducing these 10x's, we really just have a 10x to the 1 power upstairs, and these factorials reduce to leave us with an n plus 1 in the denominator. So upstairs we have 10x, downstairs n plus 1. Since n is the only thing that's actually growing, x is considered a constant in this situation. That means we have a bottom-heavy function. As n goes to infinity, this whole thing is going to go to 0. Now, this whole thing is going to converge if the ratio is less than 1. 0 is always less than 1. So what this means is we're converging infinitely in all directions. Our radius of convergence, this works for everything, so our radius of convergence is going to be infinity. Our interval of convergence is going to be all real numbers, just negative infinity, less than x, less than infinity. So there we go. For this problem, we're given the Maclaurin series for a function, this term right here. And this converges to f of x for absolute value of x less than r, where r is the radius of convergence. Okay, all that makes sense. Our first task is to use the ratio test to find r. So they're telling you, use the ratio test. Use the ratio test, Luke. We can't use the geometric series test because this is not a geometric series, because of this n down here. So using the ratio test then, we're going to have the limit as n approaches infinity of absolute value of, and now we need the n plus 1th version of this divided by the nth version of this. Now, since I have everything in an absolute value, I don't have to keep this negative around. I can just write 3 to the, and now the n plus 1th version, I'm going to have n plus 1 minus 1. So that's actually going to be 3 to the n. We're going to have an x to the n plus 1, and we're going to have an n plus 1 in the denominator. So all of that is my n plus 1th term. And now down below, I'm going to just write positive 3 to the n minus 1, x to the n, all over n. Again, don't need the negative 3 because the absolute value is going to get rid of that anyway. So now same change flip to simplify this a bit before I try taking that limit. We're going to have 3 to the n, x to the n plus 1, all that times n. That's my numerator. Down below, I have n plus 1, 3 to the n minus 1, and x to the n. I can reduce these 3's to leave me with just a 3 in the numerator, and the x is also reduced to leave me with just an x in the numerator. So I have a 3xn in my numerator, and all that's left in the denominator is n plus 1. As n goes to infinity, I can ignore this plus 1. So I essentially have a 3xn over n. N's cancel, so I just end up with absolute value then of 3x. And now to find the radius of convergence, well, I know that this series is going to converge if this common ratio, or not the common, the nth term ratio I just found is less than 1. So I'm going to set this less than 1. And to find the radius of convergence, I need to make sure that this x has a coefficient of just 1, because if you look in here, they even said an absolute value of 1x less than r. So I can get that by dividing both sides by 3. So I have absolute value of x less than 1/3, and that makes 1/3 my radius of convergence, big R. For this problem, they want us to write the first 4 non-zero terms of the Maclaurin series for f prime, and then express it as a rational function. Before I can get the first 4 non-zero terms of f prime, it would help if I had the first 4 non-zero terms of f, which I've almost got. Here are the first 3 terms. They already gave that to us. We have x minus 3/2 x squared plus 3x cubed. To get the 4th term, I just have to plug 4 for n into this formula here. So that's negative 3 to the 3rd, which is negative 27, over 4 times x to the 4th. Now I can just use the power rule to take the derivative of all this. So that's going to be 1 minus, these 2's cancel, that's just minus 3x. And here we've got 9x squared. And finally, the 4's cancel, so this is just negative 27x cubed. Now, to write this as a rational function, it helps if you recognize that this is a geometric series. We have an a1 value of 1 and an r value of, well, let's see, we keep multiplying by negative 3x each time. So I'm going to write this as a rational function just by using my infinite sum formula. That's a1 over 1 minus r. So I can write this then as 1 over 1 minus negative 3, or 1 plus 3x. And that ends up being my rational function that I needed. For the final boss battle on this free response, they want the first 4 non-zero terms of a Maclaurin series for e to the x, and then there's some more they want us to do. Let's start there, though. So this is one that you need to have memorized. This is going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and we could keep going in this pattern, but they just wanted the first 4 non-zero terms. Now they want us to use what we just wrote to come up with a 3rd degree Taylor polynomial for g of x equals e to the x times f of x about 0. Okay, well, just to review, f of x was essentially this thing up here that we've already used a few times. If I'm doing e to the x times f of x, then yeah, I'm basically multiplying this infinite series by this other infinite series. The key here is that they wanted a 3rd degree Taylor polynomial. So we only have to multiply the pieces that are going to give us exponent of 3 or lower. So just thinking about how you would go about multiplying these, you would have to use the distributive property. You'd have to have 1 times the f of x series plus x times the f of x series plus x squared over 2 factorial times the f of x series. So just think about what's actually going to give you exponent of 3 or lower. So if I take 1 and start multiplying it, I only have to multiply by these terms up to 3x cubed. So here I am writing out g of x. So we have 1 times all this stuff up to 3x cubed, because anything higher than that is going to be higher than third degree. So that'll give me something to work with. But now I also have to multiply the x from the e to the x by some things. Now looking over here, I'm going to increase the exponent by 1 when I multiply by x. So I really only need to multiply by these first two terms, x and minus 3/2 x squared. Because if I multiply x by this 3x cubed, well, that's going to give me 3x to the 4th, which is not going to be part of my third degree Taylor polynomial. And now for the last piece, I have x squared over 2 factorial to multiply by some things. But the only thing I need to multiply that by is this x here, because multiplying it by anything higher than that, again, is going to give me something higher than third degree. So I've just got x squared over 2 factorial times x. Let me multiply these out now. And note that I wrote that g of x was approximately equal to all this, just to show that, hey, yeah, I am getting a Taylor polynomial approximation. It's not the whole series. So now going from left to right, distributing here, because we do have to simplify to get at least to get no more than 1 x of each type to call it a polynomial. So we've got 1 times all this stuff, which just gives me all the stuff in this first parentheses. Next, distributing this x, we've got x squared minus 3/2 x cubed. And then over here, this is going to be x cubed, or I'll call this 1/2 x cubed. There we go. Let's go ahead and combine like terms. It's okay if your coefficients are not simplified. However, if you have multiple x squareds and x cubes out there, then again, you have not met the condition for actually writing a polynomial in terms of AP exam rigor. You do have to collect like terms in this situation. It's one of the few times you need to simplify. So let's start with the x, because that's the lowest degree. Are there any other x's out there? There are not. Go fish. So we just have x for that piece. Now for the x squareds, we have a negative 3/2 x squared and basically a 2/2 x squared. That's going to be minus 1/2 x squared. And then finally the x cubed, there's 3 of those. I'm going to combine the two out here first. Negative 3/2 and 1/2 x cubed, that's negative 2/2, which is basically negative 1x cubed. Plus the 3x cubed that's over here, that's going to be 2x cubed. And that is done.